All right, today we are going to expand our entire universe of numbers. And like any good math story, this one starts with a simple problem, a problem that our current set of numbers just can't handle. Let's dive right in.
So take a look at this equation right here. Now, if we were only allowed to work with the positive whole numbers, the ones we first learned to count with, we'd be totally stuck. There's no positive number you can add to 18 to get a smaller number like 5. To solve this, we actually need to invent a new kind of number.
And just like that, we get our answer, -13. And this one little number opens up the entire world of integers for us. All the whole numbers, positive, negative, and of course 0. So problem solved, right? Well, not quite.
What about this one? 2 times what number gives you 3? Uh-oh. All of a sudden, our nice, tidy world of integers just isn't cutting it anymore. There's no whole number, positive or negative, that can solve this. We've hit another wall. And that means our number universe has to get bigger once again. And this is exactly where we step into the huge and, frankly, fascinating world of rational numbers. These are the numbers that are designed to fill in all of those infinite gaps on the number line that sit right between the integers. So what is a rational number really? Well, the definition is actually beautifully simple. It's any number that you can possibly write as a fraction, p over q, where p and q are both integers. Now, there is one single crucial rule. That bottom number, q, can never be 0, because we all know what happens when you try to divide by 0. It just breaks math. And these images give you a perfect picture of where they live. They're literally everywhere on the number line. You've got your positive rational numbers, like 7 over 4, hanging out on the right side of 0. And then you have the negative ones, like -5 over 6, on the left. They just pack themselves in everywhere between the integers. This brings up a really interesting question. If they're filling in all these gaps, just how crowded is it on that number line? Let's just pick 2 random rational numbers, say -2/5 and 1/2. How many other rational numbers do you think we can squeeze in between them? Well, to figure this out, let's find a common denominator. So -2/5 becomes -4/10, and 1/2 becomes 5/10. And boom, just by doing that, we can suddenly see a whole bunch of numbers pop up in between. We've got -3/10, 0, 4/10. We can easily spot at least 8 of them right away. But hey, why stop there? Let's go for a bigger common denominator, maybe 20. So now our numbers are -8/20 and 10/20. And look at that! We have even more numbers to pick from, 17 of them if you count. We could keep doing this forever, just picking bigger and bigger denominators. And this leads to an absolutely wild conclusion. The number of rational numbers between any 2 points isn't just a lot, it's infinite. The number line is infinitely dense with these things. In math, we call this countably infinite, which is a whole other crazy rabbit hole to go down. But for us, the main idea is this. No matter how ridiculously close 2 rational numbers are, you can always find another one sitting between them. How cool is that? Okay, so we know what rational numbers are, and we know where they live. Now let's talk about the rules that govern their universe. You can think of these as the fundamental laws of physics for this new world of numbers we've just entered.
First up, we have something called the closure property. And I just love this closed box analogy. The question is simple. If you take 2 rational numbers out of the box and you do something to them, like add them together, is the answer you get also a rational number? Does it belong back inside the box? Or does your answer somehow escape?
Well, for addition, subtraction, and multiplication, the answer is always a big yes. You add, subtract, or multiply any 2 rational numbers, and you are guaranteed to get another rational number back. The box stays closed. But then there's division, and it has that one famous troublemaker. You can't divide by 0. And since 0 is a rational number, that one little exception means the set is not closed under division. Next up is the commutative property. This one is all about order. Pretty straightforward question. Does it matter if you calculate A plus B versus B plus A? Are you going to get the same result? Well, for rational numbers, it turns out order only matters for subtraction and division. We all know 5 minus 3 is not the same as 3 minus 5. But for addition and multiplication, you can swap the order all you want. The result is always going to be the same. They commute. All right, next is the associative property, and this one is all about grouping. If you've got three numbers in a row, doesn't matter which pair you deal with first. Is doing the first two, then the third, the same as doing the last two and then adding the first one? And hey, look at that. We see the exact same pattern as before. For addition and multiplication, you can group them however you want. It doesn't matter. They're associative. But if you try that with subtraction or division, yeah, changing the grouping will completely change your answer. So those are not associative. Now, inside this whole universe of rational numbers, there are a couple of very special inhabitants. These are numbers that play a really unique and powerful role. So let's meet the VIPs of the rational number world. So we have two identity numbers, 0 and 1. Think of 0 as the additive identity. Why? Because when you add 0 to any number, that number's identity doesn't change at all. It's kind of like the neutral element for addition. And in the same way, 1 is the multiplicative identity. Multiply any number by 1, and it just stays the same. They're like the anchors for their operations. And for every hero, there's got to be an opposite. For every single rational number, there's an additive inverse, which is really just its negative. It's the number you add to get right back to the identity 0. And for every non-zero rational number, there's a multiplicative inverse, what we usually call the reciprocal. And that's the number you multiply to get back to the other identity, 1. These inverses are what let us undo things, which is the whole key to solving equations. They just perfectly cancel each other out. So, you might be asking, why do we need to know all these rules? Are they just, abstract ideas for a math exam? No way. Understanding these properties is like having a secret toolkit. It can turn a really messy, complicated problem into something simple and, well, beautiful. Let's see it in action. Okay, check this out. At first glance, this problem looks like a complete mess of fractions, right? Trying to just power through this with brute force would be a real headache. But watch what happens when we use our new toolkit. Do you see the 2/5 here and here? Let's use that commutative property to just shuffle our terms around and get them sitting next to each other. And now for the magic trick. We use the distributive property to pull that common factor of 2/5 out front. And look at that. Suddenly, the problem is so much cleaner. All we have to do is solve the simple stuff in the parentheses, do one last bit of multiplication and subtraction, and we land right on our answer, -11/28. Way easier. So you see, these properties aren't just rules you have to memorize for a test. They are incredibly powerful tools. They show us the hidden structure of numbers, and when we use that structure, we can solve problems in a much smarter and more efficient way. And that really brings us to our final big question. Are these properties, closure, commutativity, all that stuff, are they just arbitrary rules we made up for the game of math, or are we actually discovering something much deeper, something fundamental about how quantity and logic are woven into the fabric of the universe itself? Now that is something to think about. Thanks for exploring this with me.